What if I told you that you are not just looking at distant stars, but into the distant past? And what if the very light carrying those ancient images to your eyes holds the key to understanding the fundamental rules of our reality? A cosmic speed limit that governs everything from the flow of time to the very nature of existence? For most of human history, we believed light was instantaneous, a divine switch flipped across the cosmos. But the journey to uncover the truth about the speed of light is a story of human ingenuity, revolutionary ideas, and a profound rethinking of space, time, and our place in the universe. This isn't just a story about physics, it's a story about us and the ultimate boundaries of our reality. For millennia, the nature of light was a profound mystery. To our ancestors, its speed seemed infinite, instantaneous. A candle lit in a dark room banished the shadows immediately. The sun's first rays crested the horizon, and in a flash, the world was illuminated. There was no perceptible delay. This intuitive understanding, that light was a thing of the present, a constant, unwavering presence, was deeply ingrained in human consciousness. It was a belief held by some of the greatest minds in history, a seemingly self-evident truth. But the universe is often far more subtle and wonderfully strange than our everyday experiences would lead us to believe. The first cracks in this ancient belief appeared not from a laboratory on Earth, but from the careful observation of the heavens. Our story begins in the 17th century with a Danish astronomer named Ole Rømer. Working at the Paris Observatory in 1676, Rømer was meticulously charting the motions of Jupiter's moons. In particular, he was fascinated by Io, the innermost of the 4 large Galilean moons. Io's orbit around Jupiter was like a celestial clock, with the moon disappearing behind the gas giant and reappearing with predictable regularity. Rømer used these eclipses to measure the length of Io's orbit. However, he began to notice something peculiar, a subtle yet persistent discrepancy in his timings. He observed that when the Earth, in its own orbit around the Sun, was moving towards Jupiter, the eclipses of Io seemed to happen slightly ahead of schedule. Conversely, when the Earth was moving away from Jupiter, the eclipses appeared to be delayed. This was a puzzle. The orbits of celestial bodies were thought to be governed by precise, unchangeable laws. What could possibly be causing this apparent speeding up and slowing down of Io's celestial dance? Rømer considered various possibilities. Was Jupiter's orbit itself irregular? Was there some unknown force at play? But the pattern was too consistent, too closely tied to the Earth's position relative to Jupiter. Then, in a stroke of brilliant insight, Rømer realized that the discrepancy had nothing to do with the moon's orbit at all. The variable was not the event, but the time it took for the light from that event to reach his telescope. He deduced that when the Earth was on the side of its orbit closer to Jupiter, the light from Io had a shorter distance to travel. When the Earth was on the far side of its orbit, the light had to traverse the entire diameter of Earth's orbit to reach his eyes, and this extra distance was causing the delay. The light, he concluded, must have a finite, measurable speed. Based on his observations, Rømer calculated that it took light about 22 minutes to cross the diameter of Earth's orbit. While the exact diameter of Earth's orbit wasn't precisely known at the time, his calculation was in the right ballpark. Using modern values for the astronomical unit, Rømer's data would yield a speed of light remarkably close to the currently accepted value of approximately 299,792 kilometers per second. This was a revolutionary discovery, the first real chink in the armor of the infinite speed of light theory. For the first time, humanity had a tangible measure for what was once considered immeasurable. Rømer's discovery, however, was not immediately embraced by the scientific community. It was a radical idea that challenged long-held beliefs. It would take decades of further observations and experiments to solidify the concept of a finite speed of light. But the seed of a new understanding had been planted. The stage was set for future generations of scientists to refine this measurement. To probe the nature of light, with ever-increasing precision. One such scientist was Albert A. Michelson, an American physicist who dedicated a significant portion of his career to measuring the speed of light with unparalleled accuracy. Throughout the late 19th and early 20th centuries, Michelson conducted a series of brilliant experiments using sophisticated arrangements of mirrors and rotating prisms to send beams of light over long distances and measure their travel time. His experiments, conducted in various locations from the U.S. Naval Academy to the mountains of California, produced increasingly precise values for the speed of light. Michelson's work was a testament to the power of meticulous experimentation, pushing the boundaries of what was technologically possible. But in his quest for precision, Michelson, along with his collaborator Edward Morley, stumbled upon a puzzle far more profound than they could have imagined. Their most famous experiment, the Michelson-Morley experiment of 1887, was designed to detect the luminiferous ether, a hypothetical invisible medium that was believed to permeate all of space and carry light waves, much like air carries sound waves. If this ether existed, then the speed of light should appear to change, depending on the Earth's motion through it. As the Earth orbits the Sun, it should be moving through this ether, creating an ether wind. They expected to measure a difference in the speed of light when a beam was pointed in the direction of the Earth's motion, compared to when it was pointed perpendicular to it. To their astonishment, they found no difference whatsoever. The speed of light was the same in all directions, regardless of the Earth's motion. They repeated the experiment at different times of the year, when the Earth was moving in different directions in its orbit. But the result was always the same: a null result. The speed of light appeared to be an unshakable constant. This seemingly simple observation was a bombshell that would send shockwaves through the world of physics. It directly contradicted the principles of classical mechanics, which had reigned supreme for over 2 centuries since the time of Isaac Newton. The Michelson-Morley experiment had inadvertently uncovered a fundamental truth about the universe, a truth that would require a complete rewriting of our understanding of space, time, and reality itself. The puzzle was set, and the world was waiting for a mind bold enough to solve it. The late 19th century was a period of great confidence in the world of physics. The laws of motion and gravity laid down by Isaac Newton, and the theories of electricity and magnetism developed by James Clerk Maxwell, seemed to describe the workings of the universe with remarkable precision. Yet the baffling result of the Michelson-Morley experiment cast a long shadow over this otherwise triumphant picture. The fact that the speed of light remained constant, irrespective of the observer's motion, was a profound anomaly that defied all conventional wisdom. According to classical physics, speeds are relative. If you're on a train moving at 100 kilometers per hour, and you throw a ball forward at 20 kilometers per hour, someone standing on the platform would see the ball moving at 120 kilometers per hour. It's simple addition. But light refused to play by these rules. Whether you were on a rocket hurtling towards a light source or speeding away from it, you would always measure its speed to be the same. This perplexing constancy led many physicists down a rabbit hole of complex and ultimately convoluted explanations. The idea of the luminiferous ether was so entrenched that scientists proposed elaborate theories to save it. Some suggested that the Earth dragged the ether along with it, which is why no ether wind was detected. Others, like George Fitzgerald and Hendrik Lorentz, proposed that objects moving through the ether physically contract in the direction of their motion, and that clocks on these objects slow down. This length contraction and time dilation would conspire to make the speed of light appear constant. While these ideas were mathematically sound and would later prove to be aspects of a deeper truth, they were ad hoc solutions, designed to patch up an old theory rather than to reveal a new one. The universe, it seemed, was whispering a secret, but no one was quite speaking its language. Enter Albert Einstein. In 1905, while working as a humble patent clerk in Bern, Switzerland, this 26-year-old visionary offered a perspective so radical, so elegantly simple, that it would forever change the course of science. Einstein didn't try to explain why the speed of light was constant with complex mechanisms like the ether. Instead, he accepted it as a fundamental principle of the universe. He proposed a new theory, his special theory of relativity, built upon two deceptively simple postulates. The first postulate, the principle of relativity, states that the laws of physics are the same for all observers in uniform motion. This means that you cannot perform any experiment to determine whether you are at rest or moving at a constant velocity. Imagine you're in a perfectly smooth-riding train with the window shades down. You could drop a ball, and it would fall straight down. You could pour a cup of coffee, and it would behave exactly as it would if the train were stationary. There is no absolute rest in the universe. All uniform motion is relative. This idea was not entirely new. It had roots in the work of Galileo, but Einstein elevated it to a cornerstone of his new physics. The second postulate was the truly revolutionary one. The speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. This was a direct embrace of the Michelson-Morley result, turning a confusing experimental finding into a fundamental law of nature. Einstein had the audacity to say, "Let's not try to explain this away. Let's see what happens if we take it as a given." From these two simple yet powerful postulates, a whole new understanding of reality emerged. The consequences were staggering. If the speed of light is to remain constant for everyone, then something else must be flexible. That something, Einstein showed, was space and time itself. He demonstrated that time can slow down and space can contract, depending on your relative motion. The faster you move through space, the slower you move through time. This is not a trick of perception. It is a real physical effect. Time, space, and even mass were no longer the absolute, unchanging quantities that Newton had envisioned. They were relative, intertwined in a way no one had ever imagined. Einstein's special theory of relativity was a complete paradigm shift. It did away with the need for the ether and provided a new, more elegant framework for understanding the universe. It revealed that the constancy of the speed of light was not an anomaly, but a window into a deeper, more profound reality. A reality where the familiar, intuitive world of our everyday experience is just a small part of a much grander, more dynamic cosmos. The patent clerk from Bern had not just solved a puzzle. He had provided humanity with a new language to describe the universe, and in doing so he had become the architect of a new era in our quest for knowledge. Einstein's theories didn't just redefine our understanding of space and time. They also imposed a new, ultimate law on the cosmos, a universal speed limit. Nothing with mass, he demonstrated, can ever reach the speed of light. This isn't just a technological challenge to be overcome with a more powerful engine. It's a fundamental property woven into the very fabric of space-time. To understand why, we need to delve into one of the most famous equations in all of science, E1 mc2. This elegant equation, a direct consequence of special relativity, reveals a profound and intimate connection between energy, E, and mass, m. It tells us that mass and energy are two sides of the same coin, that they are, in a sense, interchangeable. The c2 in the equation is the speed of light squared, and because the speed of light, c, is such an enormous number, this equation tells us that a tiny amount of mass can be converted into a tremendous amount of energy. This is the principle that powers nuclear reactors and atomic bombs, where a small fraction of the mass of uranium atoms is converted into a colossal release of energy. But this equation also works in the other direction. Just as mass can be converted into energy, energy can be converted into mass. And this is the key to understanding the cosmic speed limit. When you apply energy to an object to make it move faster, to accelerate it, you are increasing its kinetic energy, the energy of motion. According to classical Newtonian physics, if you keep applying a constant force, the object should continue to accelerate indefinitely. But in Einstein's universe, something else happens. As an object approaches the speed of light, the energy you pour into it starts to manifest in a different way. Instead of just making the object go faster, more and more of that energy is converted into mass. Imagine you are pushing a cosmic shopping cart. At low speeds, it's easy. A steady push results in a steady increase in speed. But as you start to get closer and closer to the speed of light, you'd find that the shopping cart gets heavier and heavier. Its mass, its resistance to being accelerated further, increases. This increase in relativistic mass is not because the object is accumulating more particles. It's because its energy of motion is contributing to its total mass. This effect is negligible at the speeds we experience in our daily lives. A car on the highway, a commercial jet, or even the fastest spacecraft we've ever built are all moving at a tiny fraction of the speed of light. So the increase in their mass is infinitesimal. But as you approach light speed, the effect becomes dramatic. At 90% of the speed of light, an object's mass has more than doubled. To push it a little faster, you need to supply even more energy, which in turn increases its mass even further. At 99.9% of the speed of light, an object's mass is over 22 times its rest mass. This creates a vicious cycle of diminishing returns. The faster you go, the heavier you get, and the more energy it takes to achieve the next small increment of speed. As you get infinitesimally close to the speed of light, your mass and the energy required to accelerate you further would approach infinity. Since there isn't an infinite amount of energy in the universe, it is impossible for any object with mass to ever reach the speed of light. It's a cosmic asymptote, a finish line you can forever approach but never cross. This isn't just a theoretical concept. Particle accelerators like the Large Hadron Collider, LHC, at CERN, are real-world demonstrations of this principle every day. In these massive underground rings, protons are accelerated to 99.9999% of the speed of light. The cosmic speed limit, therefore, is not a simple barrier that you can punch through. It's a fundamental consequence of the deep relationship between mass, energy, and the structure of reality. The universe itself enforces this law, a law that ensures a certain order and structure to the cosmos. It's a law that has profound implications for the nature of time, the possibility of interstellar travel, and the very fabric of space-time. So why does the universe have this built-in speed limit? Why does adding energy to a moving object make it heavier instead of just faster? The answer lies in one of the most mind-bending concepts to emerge from Einstein's work. The idea that space and time are not separate entities, but are instead woven together into a single, four-dimensional continuum called space-time. This is where the story moves from the realm of motion and energy to the very geometry of reality itself. Think about your own movement. At any given moment, you can move in three spatial dimensions: forward or backward, left or right, up or down. But Einstein revealed that there is a fourth dimension we are all constantly traveling through: time. And here's the crucial insight. All objects in the universe are always traveling through space-time at a constant speed, the speed of light. This might sound absurd. We are clearly not all zipping around at the speed of light. But that's because this total motion through space-time is divided between the three dimensions of space and the one dimension of time. When you are sitting perfectly still in your chair, you are not moving through space at all. In this state, all of your motion is dedicated to traveling through the time dimension. You are moving into the future at the maximum possible rate, 1 second per second. Now imagine you get up and start walking. As you begin to move through space, you are diverting some of your total motion from the time dimension into the spatial dimensions. This means that your passage through time must slow down relative to someone who remains stationary. The faster you move through space, the more of your space-time motion is allocated to your spatial velocity, and consequently the slower you travel through time. If you could, hypothetically, travel through space at the speed of light, all of your motion would be dedicated to the spatial dimensions. You would have no motion left for the time dimension, and for you, time would completely stop. A photon, a particle of light, travels at the speed of light, and from its perspective, its entire journey across the universe is instantaneous. This effect, where time slows down for a moving observer, is known as time dilation. And it is not just a theoretical curiosity, it's a proven, measurable phenomenon. One of the most compelling pieces of evidence comes from experiments with atomic clocks, the most accurate timekeeping devices ever created. In 1971, in the Haffel-Keating experiment, physicists flew several atomic clocks on commercial airliners around the world. When the clocks returned and were compared with a reference clock that had remained on the ground, the clocks that had been flying were found to be running slightly slower, by a few nanoseconds. The difference was tiny, but it perfectly matched the predictions of Einstein's theory. Today, the satellites of the Global Positioning System, GPS, have to constantly account for the effects of time dilation. The satellites are moving at high speeds in orbit, and their onboard clocks run slightly slower than clocks on Earth. If this effect wasn't corrected for, the GPS system would accumulate errors of several kilometers per day, making it essentially useless. Another fascinating proof of time dilation comes from the world of particle physics. Cosmic rays, high-energy particles from space, constantly bombard the Earth's upper atmosphere, creating a shower of secondary particles. Among these are particles called muons. Muons are unstable and have a very short lifespan, typically decaying in about 2.2 microseconds when at rest. Based on this lifespan, even if they were traveling at nearly the speed of light, they should only be able to travel about 660 meters before they decay. This means we should not be able to detect them at the Earth's surface. Yet, we detect them in abundance. The reason is time dilation. Because the muons are traveling at such high speeds, their internal clocks are running much slower from our perspective. Their lifespan is extended, allowing them to survive the journey from the upper atmosphere to the ground. In a very real sense, they live longer because they are moving faster. This leads us to the famous twin paradox. Imagine a pair of twins. One, the Earth twin, stays at home. The other, the traveling twin, embarks on a journey to a distant star in a high-speed rocket. When the traveling twin returns, they will find that they have aged less than their Earth-bound sibling. From the perspective of the Earth twin, the traveling twin's clock was running slow throughout the journey. The traveling twin, by moving through space, has traveled into the Earth's future. This is not science fiction. It is a direct consequence of the nature of space-time. It is a form of one-way time travel. The speed of light, therefore, is not just a limit on how fast you can move through space. It's a fundamental constant that dictates the relationship between space and time. It is the conversion factor that tells us how much of our motion through time we must trade for motion through space. The cosmic speed limit is a consequence of the fact that we are always, moving through space-time at a fixed rate, and this journey through the fourth dimension is the very essence of our experience of time. Ultimately, the reason the universe has this strict speed limit, this unbreakable connection between space, time, and mass, is to protect its own logical consistency. The speed of light is not really about light itself. It is the speed of causality. It is the maximum speed at which information, any cause and effect relationship, can propagate through the universe. To understand this, we need to think about the order of events. Imagine you throw a baseball and it breaks a window. The cause, throwing the ball, happens before the effect, the window breaking. This is a fundamental principle of our reality. Cause always precedes effect. Now, what would happen if you could send a signal faster than light? Let's say you have a device that can send a message to a spaceship orbiting a star 10 light-years away, and the message arrives instantly. From your perspective, you send the message, and it's received at the same moment. But remember, according to relativity, there is no absolute now that everyone in the universe agrees on. For an observer on another spaceship, moving at a high speed relative to both you and the distant star, the order of events could look very different. Due to the way spacetime is structured, it's possible for that moving observer to see the message being received by the spaceship before you even sent it. This opens the door to all sorts of paradoxes. If the spaceship received your message before you sent it, they could send a message back to you, also faster than light, that arrives before you sent your original message, telling you not to send it. So, would you send it? If you don't, then they would never have received it and sent the warning back. This is a classic grandfather paradox, where an effect eliminates its own cause, creating a logical contradiction that would unravel the fabric of reality. The universe prevents these paradoxes by enforcing the cosmic speed limit. By ensuring that no information can travel faster than light, the universe guarantees that the order of cause and effect is preserved for all observers, regardless of their relative motion. This concept is often visualized using a light cone. Imagine an event, say a firecracker exploding. The light from that explosion expands outwards in a sphere at the speed of light. If we represent this on a space-time diagram, with time as the vertical axis and space as the horizontal axis, the expanding sphere of light forms a cone. This is the future light cone of the event. Any event that happens inside this cone can be influenced by the firecracker explosion. Events outside the cone are too far away in space and too close in time for the light, and therefore any information from the explosion to have reached them yet. They are causally disconnected. Similarly, there is a past light cone, representing all the events that could have influenced the firecracker explosion. The speed of light, therefore, defines the boundaries of causality. It separates the parts of the universe we can interact with and be influenced by from the parts we cannot. It ensures that the universe unfolds in a logical, orderly fashion, where the past influences the present, and the present influences the future, but the future cannot influence the past. This chronology protection, as some physicists call it, seems to be a fundamental feature of our cosmos. The speed of light is not just a physical barrier, it's a logical one. It's the universe's way of preventing itself from descending into chaos and paradox. It is the law that keeps the story of the cosmos coherent. Of course, the idea of breaking this ultimate speed limit has been a tantalizing dream for humanity, a cornerstone of science fiction. The vast distances between stars make interstellar travel a daunting, centuries-long endeavor at sublight speeds. So, what about the theoretical loopholes? Do concepts like warp drives and wormholes, which seem to offer a way to cheat the cosmic speed limit, have any basis in reality? The answer, according to our current understanding of physics, is a qualified yes, but with a mountain of seemingly insurmountable obstacles. Let's start with wormholes, or as they are more formally known, Einstein-Rosen bridges. These are theoretical tunnels through space-time, shortcuts that could connect two distant points in the universe, or even two different points in time. The equations of Einstein's general theory of relativity do indeed permit solutions that describe such structures. However, there's a catch, and it's a big one. For a wormhole to be traversable, meaning something could actually pass through it, it would need to be propped open by a type of exotic matter with some truly bizarre properties. This exotic matter would have to possess negative energy density, or in simpler terms, negative mass. It would be gravitationally repulsive, pushing things away rather than pulling them in. While some quantum effects can create tiny, fleeting pockets of negative energy, we have never observed any stable form of exotic matter, and it's not clear if it can exist in the quantities needed to sustain a human-sized wormhole. Furthermore, even if you could create such a wormhole, it would likely be catastrophically unstable. The slightest disturbance, even the act of sending a single photon through it, could cause it to collapse into a black hole. Then there's the Alcubierre warp drive, a concept proposed by physicist Miguel Alcubierre in 1994. This theoretical drive would not propel a spaceship through space faster than light. Instead, it would warp spacetime itself around the ship. It would work by contracting the space in front of the ship and expanding the space behind it, creating a warp bubble. The ship itself would remain stationary within this bubble, like a surfer riding a wave of spacetime. Since spacetime itself can expand or contract at any speed, the bubble, and the ship within it, could theoretically travel at arbitrarily high velocities, effectively bypassing the local speed of light limit. It's an incredibly clever idea, but it too comes with some serious roadblocks. Firstly, like wormholes, the Alcubierre drive would require vast amounts of exotic matter with negative energy density to create the warp bubble. In fact, some calculations suggest it would require an amount of energy equivalent to the mass energy of the entire observable universe, or even more. Secondly, there are causality paradoxes. A ship with a warp drive could potentially be used to travel backward in time, creating the same logical contradictions that the speed of light limit is there to prevent. There are also some rather nasty side effects. For example, any particles the bubble swept up on its journey would be released in a devastating burst of high-energy radiation upon arrival, obliterating anything at the destination. While these concepts are fascinating theoretical playgrounds for physicists, they currently remain firmly in the realm of science fiction. The universe, it seems, has built-in protections to prevent these kinds of shortcuts. This doesn't mean the universe is without its own subtleties and apparent contradictions. The cosmic speed limit operates in some nuanced and fascinating ways, particularly in the bizarre world of the quantum realm and on the vast scales of cosmology. One of the most famous quantum phenomena is entanglement, which Einstein famously called spooky action at a distance. When two particles like electrons or photons become entangled, their fates become linked, no matter how far apart they are. If you measure a property of one particle, like its spin, you instantly know the corresponding property of the other particle, even if it's on the other side of the galaxy. This seems to suggest some kind of instantaneous communication, a clear violation of the speed of light. However, the key here is that while the correlation between the particles is instant, you cannot use entanglement to transmit information faster than light. Imagine you and a friend each have one of a pair of entangled coins. You know that if your coin lands heads, your friend's will be tails, and vice versa. You flip your coin, and it comes up heads. You instantly know your friend's coin is tails. But this doesn't transmit any new information. Your friend doesn't know the result until they look at their own coin, or until you send them a message through conventional, light-speed-limited means. You can't control the outcome of your coin flip to send a Morse code message, for example. The outcome is random. So while quantum entanglement is a deep and mysterious feature of reality, it respects the principle of causality. The universe is spooky, but it's not paradoxical. On the other end of the scale, we have the expansion of the universe itself. In 1929, Edwin Hubble discovered that distant galaxies are all moving away from us, and the farther away they are, the faster they are receding. For very distant galaxies, this recession speed can actually exceed the speed of light. This might sound like a direct violation of Einstein's theory, but it's not. The key is that these galaxies are not moving through space faster than light. Rather, the fabric of space between us and those galaxies is expanding, carrying the galaxies along with it. A good analogy is to imagine dots on the surface of an uninflated balloon. As you inflate the balloon, the dots all move away from each other. From the perspective of any one dot, the other dots are receding. And the farther away a dot is, the faster it appears to be moving away, because there is more balloon surface expanding between them. The dots themselves are not moving across the surface of the balloon. They are being carried apart by the expansion of the balloon itself. Similarly, distant galaxies are not breaking the cosmic speed limit in their local patch of space. They are simply riding the wave of an expanding universe. This also means that there is a cosmic horizon, a distance beyond which we can never see, because the galaxies there are receding from us faster than their light can travel towards us. So we see that the cosmic speed limit, this constant c, is far more than just a number on a physicist's chalkboard. It is a fundamental pillar of our reality, a rule that is woven into the very fabric of the cosmos, from the smallest quantum scales to the largest cosmological ones. The finite speed of light has a profound and beautiful consequence. It turns the universe into a vast time machine. When you look up at the night sky, you are not seeing the stars as they are now, but as they were in the past. The light from our nearest star, Proxima Centauri, takes over 4 years to reach us. So we see it as it was 4 years ago. The Andromeda Galaxy, our closest major galactic neighbor, is about 2.5 million light-years away. The light we see from it tonight began its journey when our early human ancestors were first walking the Earth. And with powerful instruments like the James Webb Space Telescope, we can peer even deeper into cosmic history, seeing galaxies as they were over 13 billion years ago, just a few 100 million years after the Big Bang. Looking out into space is literally looking back in time. The cosmic speed limit is our window to the universe's past. This fundamental constant is not an arbitrary number. Its value is deeply connected to other fundamental constants of nature. It determines the strength of the electromagnetic force, the force that governs everything from the way atoms hold together to the propagation of light itself. If the speed of light were different, the laws of chemistry would be different, and the existence of life as we know it might be impossible. It is, as we've seen, the ultimate conversion factor between mass and energy in E2mc2, underpinning the processes that power stars and create the elements necessary for planets and people. And its influence extends even to the force of gravity. According to Einstein's general theory of relativity, gravity is not a force that acts instantaneously across distances, but rather a curvature of spacetime caused by mass and energy. When a massive object moves, it creates ripples in this spacetime fabric, which propagate outwards like waves on a pond. These are gravitational waves, and Einstein predicted that they should travel at the speed of light. For a century, this was a theoretical prediction. But in 2017, humanity witnessed a spectacular confirmation. Astronomers detected both gravitational waves and light from the collision of two neutron stars. The two signals arrived at Earth at almost exactly the same time after a journey of 130 million years, confirming that gravity indeed propagates at the speed of light. The cosmic speed limit, therefore, is not just a rule. It is a foundational principle of reality. It is the constant that defines the relationship between space, time, mass, and energy. It is the speed of causality, the guardian of logical consistency, and the metronome that sets the rhythm of the cosmos. It is the reason why looking up at the stars is a journey into the past, and it is the unbreakable law that shapes our present and our future. So what is the lesson for us in all of this? This journey from a simple observation of Jupiter's moons to the very fabric of space-time reveals a profound truth about the process of discovery. It shows us that our common sense, intuitive understanding of the world is often just a small slice of a much larger, stranger, and more wonderful reality. The universe is under no obligation to make sense to us on our limited human terms, but by being curious, by questioning assumptions, and by daring to imagine new possibilities, we can begin to peel back the layers of the cosmos and glimpse the elegant and profound laws that govern it all. The story of the cosmic speed limit is a reminder that there are fundamental rules to the universe, and understanding those rules allows us to see our world with new eyes. It teaches us that time is not as simple as a ticking clock, that space is more than just an empty void, and that we are all on a constant journey through a four-dimensional reality. In our daily lives, we may not be traveling at near-light speeds, but the principles of relativity are at work all around us, in the technology we use like GPS, and in the starlight we see at night. This knowledge gives us a deeper appreciation for the intricate and interconnected nature of our universe. It encourages us to remain humble in the face of the vast unknown, and to continue asking questions, because as this story shows, sometimes the biggest revolutions in understanding come from questioning the things we think are most obvious. I hope this journey to the cosmic speed limit has expanded your own universe a little bit today. It leaves us with some incredible questions to ponder. If you could take a trip on a near-light speed rocket and travel into Earth's future, where would you want to go and what would you hope to see? And what do you think is the next unbreakable law of physics that a future Einstein might show us is actually flexible? I'd love to read your thoughts in the comments below. Thank you for joining me on this exploration of one of the most fundamental aspects of our reality. I wish you all good health, a clear mind, and a sky full of wonder. If you enjoyed this journey and want to continue exploring the biggest questions of the cosmos, don't forget to like, share, and subscribe to the channel. Until next time.